Future Earth science missions will follow new observing strategies to combine observations from large satellites, small satellites, as well as in situ and airborne platforms, all dynamically exchanging information to coordinate observations towards scientific objectives. These new observing strategy-style missions, however, pose a challenge because the models of the constituent nodes are contributed by different disciplines and across organizational boundaries, posing significant integration challenges. This paper discusses a service-oriented architecture where individual models are abstracted to loosely coupled services within a service-oriented application. If services are simulators, this is also called a co-simulation architecture. In this paper, we only investigate cases where services communicate through simple HTTP requests. Our example case considers 4 different services: an environmental state service that represents the initiation and spread of a fire, a propagation state service that models the movement of spacecraft, an operations state service that models the operation of spacecraft, including detection of fire events, and also a visualization service that illustrates a mission for users.
Okay, so let's have a demonstration here of some of the back-end services. I'm going to go ahead and start the script, and then we'll talk about what's shown here. So in this particular simulation, we've called the environment state service to generate wildfire time series data, and then we've assembled an ad hoc constellation by propagating the orbits of 3 separate satellites, NOAA 20, Suomi NPP, and GOES-16. We then call a mission element state service, in this case wildfire detection, to determine when detections can occur for each of these 3 satellites in our ad hoc constellation. In this line here, then, we assemble the performance of each of the satellites to a collective constellation performance to determine when the first detection by any of the platforms or the constellation could occur. In this case, it's 100 seconds after ignition of the wildfire. So it's important to note that while in this particular implementation, all of the services have been written in Python and we're running everything on the same machine, that each of these services could be run asynchronously at different locations so long as the formats of the inputs and outputs have been specified. And in this work, the full implementation used JSON. So let's go ahead and take a look at that now. So we're going to go ahead and start our Flask server. And then if we just open up our web browser and navigate to the URL we've specified, we can see that the simulation does indeed kick off here with visualization services. You can see we have 3 satellites in our constellation, GOES-16 and then the 2 LEO satellites, as well as a wildfire location specified by this white circle. So if we go ahead and run the visualization for the simulation, we'll see that as the wildfire intensifies, it turns yellow, and GOES-16, once it achieves an observation, turns green, and these other satellites will turn green as well while they're observing the wildfire successfully. So you can see one of the LEO satellites just turned green. Okay, but we can actually use this tool in a broader context by specifying constellations that don't yet exist. So you can see in this script here, we've specified a constellation with 5 satellites per plane, 12 planes, a 90-degree inclination, and we've specified the altitude elsewhere, and combined the performance of this imaginary constellation with that of existing platforms to determine collective performance of existing and non-existing systems that can be simulated across different platforms.
Our application case evaluated 3 satellite constellations in the context of a fire detection mission. The first constellation was comprised of existing NOAA satellites. The second constellation was comprised of 60 small satellites arranged in 12 planes and 5 satellites per plane. The third constellation combined all the elements of the other 2 constellations. Each constellation was evaluated over 1,000 trials with varying fire ignition conditions. The results show that the NOAA satellites do very well at detecting rapidly intensifying fires with an average detection time of just 160 seconds. However, slowly growing fires are much more difficult for the NOAA satellites to detect due to the relatively low revisit rate of the VIR sensors on the Suomi NPP and NOAA 20 satellites. The small satellite constellation, on the other hand, has an average detection time that's slightly greater, but detects all fires in less than 23 minutes. The joint architecture combines the best features of both systems with an average detection time of only 100 seconds and still detecting all fires in less than 23 minutes. This application case demonstrates how the loosely coupled simulation services of a co-simulation environment can be used to perform concept evaluations, which require information and expertise from a multitude of sources.